it is my pleasure to welcome Eun-Ah Kim, who once again kindly agreed to give a talk about machine learning of quantum emergence. And I have Eun-Ah, I have unmuted you, and yes, your screen is on. Everything is working.
Wonderful. Hi, can you see me and hear me?
Yes.
Okay, great. It's a pleasure to be in this session. So I want to talk about machine learning quantum emergence. And there will be two main topics, but I want to start by kind of giving some introduction. So this is an example of emergence here. This is a social phenomena, but the emergence we are interested in, if you talk about quantum phenomena, is at the level of electrons. And if you are only considering perfect crystal.
Excuse me, sorry. Perhaps
yeah?
if possible, if you would like, would you like to put your to turn your video on, because there's your screen, but your camera is off, or? It's
sorry.
Very important.
What was that?
Would you like to turn your camera on, because
oh, camera, yes. Is that working now?
Yes.
Let me see.
Can you see me?
Yes, yes.
Yes,
Yeah.
it's working.
Yeah, very good. Thank you very much.
All right. So, right. So if you only consider a perfect crystal, you only have to think about unit cell. And even when your unit cell is pretty big, as in this Pyrochlore material, the amount of information in a material for a perfect crystal is pretty small. However, in the real world, there are defects, vacancies, stacking faults, and once you start to take into account that we are interested in the distribution of electrons, we're interested in the spin state, when all of these things are combined, the actual information content of the material becomes extensive. Instead of just thinking about the unit cell, we'll have to think about the extensive system. And given the number of degrees of freedom, the amount of information in a given sample that we want to study could be as big as square of the entire written print collection at the Library of Congress. So given the amount of this huge amount of information, or the phase space, it ought to be very difficult to be able to make predictions and understand properties. Nevertheless, we would like to be able to understand when we see a given material, whether it's going to be a topological insulator, whether it's going to be a superconductor, we would like to be able to understand and control. And therefore, there have been a lot of effort in the community to try to gain more information out of the materials, or think of a new system that we can study better with a better control. So with all these efforts, now we are at a age where we are managing to retain a lot more information from these material systems, but now the major bottleneck is becoming data-driven challenges. So for instance, in quantum systems that are now available, we can have sizable number of qubits, but when we want to understand what kind of state the system is actually in, we need exponentially large number of measurements in order to be able to characterize. So this is an example of a data-driven challenge. Tunneling density of states in 1960s was measured through a macroscopic tunnel junction, as this shown here. And what one would measure was a curve. And we understand every aspect of this curve, not just the suppression, not only the peak, but we also understand these little wiggles. We have models that are very satisfactory about this entire curve. But we wanted to understand more about the materials. We discovered more complex materials. And come to 2000, the amount of information we have is not a single curve for a given sample, but a whole big selection of curves, or a layer of images. And we don't have a satisfactory model to describe these data sets, nor would we have hope in coming up with such a model. X-ray diffraction in 1913. This is a snapshot from the original paper that was a Nobel Prize winning by father Bragg and son Bragg, Bragg and Bragg. And what was described in this paper is perhaps the first successful example of what we now call forward modeling. So the kind of data they were looking at in this paper was again this kind of curve. They are changing the incident angle of the X-ray beam, and they're measuring the intensity. And as they change the tilt angle, there's only one angle that they're changing, and they're obtaining these kind of curves. And these curves were successfully explained by this forward model that Bragg and Bragg put forth, which gives rise to a Bragg condition that we now learn in introductory physics. However, now we come to 2020, the way we do the measurement is not just a single curve, but this is a setup, for instance, is being used at Argonne National Lab or other facilities worldwide. For a given angle, you can scan so many Brillouin zones because of your intensity, and now you change that angle with 0.1 degree increments. Here we're showing 10 degrees, just otherwise it's too busy, but 0.1 degree increment is giving you a very comprehensive view of many, many thousands of Brillouin zones. Now, again, we don't have a capacity to handle this kind of space with forward modeling in the spirit of Bragg and Bragg. So what are we going to do when you get this kind of big data set? All the information that we want to know about the material must be in here, but we don't know how to zoom into it. We don't know how to extract it. So facing these kind of data-driven challenges, what my group have been really working hard on was to try to form a bridge between experimental data that's complex and rich, complex and big, and theoretical understanding, our principles that we know how to think about that are simple. We're trying to find a bridge through data science tools. These are a collection of efforts that's been going on in my group. Now I'm going to talk about two examples. That is the scanning tunneling microscopy work that was published in Nature last year, and currently ongoing nearly completed preliminary results in X-ray data analysis. But more on this will be in the 10-minute talk, would have been in a 10-minute talk by my student, Jordan Vendely. The slides are now available through the APS abstract server system. So I recommend that you take a look at that. We also looked at resonant ultrasound spectroscopy, which was a hard kind of data to model. This was in collaboration with Brad Ramshaw. It just has shown up as scientific advances today. You can also find our work on analyzing scanning tunneling electron microscopy data in the talk of Michael Meddy in session W39. We're also looking at quantum state tomography on the IBM-Q data. You can find that in Peter Cha's talk. And we're looking at the non-Fermi liquid transport in simulated data of itinerant quantum fermion models. Now, this is sort of a survey of all these different activities that are going on. And over the course of last couple of years, working on various interesting data challenge problems, one thing that we learned, one lesson we learned that I would like to share with everybody in case people are interested in entering this effort is something very, very basic, very obvious, which is machine learning tools are tools. These are data-driven tools, data science tools, and like any other tools, they are purpose-driven. So these are two very useful, very powerful tools, drill and a chainsaw. Each are very useful tools, but there are tasks that you want to use the drill for, and those tasks are likely not the right task for the chainsaw. So when you have a problem that you're interested in, you want to think about, and most likely, the data science tools as they are developed may not be specifically developed for your purpose, your problem, because we as physicists, we own the problems and we own the data. But you want to find a tool that seems to be closest to your purpose. And sometimes if it's not going to be the most powerful tool, most expensive tool out in the market, you also want to pay attention to making sure that perhaps Hammer is the best tool for what you need. So that's just generally being discerning, thinking carefully about what kind of tool would best work for your purpose, I think is an important thing to take into account for your success. So now let me talk about supervised machine learning for hypothesis testing. The problem we were interested in here was trying to gain sense out of local motifs in scanning tunneling spectroscopy data of pseudogap states in high-TC cuprates. And the work was really driven by my former postdoc, Yi Zhang, who is now faculty at Peking University. And I had the pleasure of collaborating with all these collaborators and my longtime collaborator, Seamus Davis. You can find more details of this work in this paper. So what is the question? When many experimentalists, when they finish their long and hard work and have their data, they want to understand, they want to come to some decision about which theory best describes their data. For instance, this is scanning tunneling spectroscopy data of pseudogaps data high-TC cuprates. And looking at this, we've long wanted to understand whether it is best described as a weak coupling K-space starting point or from strong coupling real space starting point. And the conventional approach to this kind of data is to do Fourier transform because there is a modulated pattern that's visible to our eye, and then you want to try to compress Fourier transform down to the peak location of a line cut. So now you take this data and Fourier transform, and what you get is this kind of messy distribution. You can see, yes, there is some activity somewhere between the center and the corner of the Brillouin zone, but it's very broad. This is a line cut along this red line, and you can see that it is broad and very jagged. This jaggedness is not only because the field of the small field of view, but in part has to do with abrupt natures of the structures, motifs that are in the system. However, when our eyes look at this data set, we readily recognize some sort of motif there. So we were interested in trying to come to a decision about these motifs. What is the right starting point to think about? What's the hypothesis that would better describe the data? And this hypothesis that we're trying to discriminate against each other has to do with the long-standing question of how to best understand the enigmatic pseudogap phase. So once we want to think about the patterns, we can have theory-guided models of charge density wave. We know a lot about charge density wave. We know how to model it as a complex order parameter with amplitude and phase. We know what kind of noise there can be. There can be phase noise. There can be topological defects. There can be noise in the amplitude. So we can have theory-driven models that can implement our hypothesis into something that looks like pictures. However, trying to describe the entire feature of the data is kind of hopeless. One can still think about what would be different wave vectors that are representative. And these are 4 wave vectors we could think of. These are the candidates that we want to have them compete. And one of them is coming from real space perspective because it is commensurate. And the other 3 are coming from K-space perspective because part of the K-space perspective, recoupling perspective, is to allow the wave vector to vary with doping. So that's another thing that we will be looking for. So now we want to look for a machine or tool that can be trained to make a sensible decision. And that's what we're using here is a very simple artificial neural network. And to think about, to talk about how neural network is trained to make a decision, I'd like to show the thought process when one has to make a decision. And this is a moment that you can imagine somebody who is under training has to make a decision. This is a kid who just dropped ice cream. And the kid would be taking inputs. How long has it been? Is mom watching? If the mom is the bad cop in the family, like in my family, how sweet is it? How green is it? The child is taking these kind of inputs. And the decision the child has to make is not between what is the better hypothesis for the high TC cuprate, but something simpler, like should I pick it up and eat it or let it be? But nevertheless, the process of decision making is that you take these inputs, and the inputs will be taken with different input components, input vector components will be weighed differently depending on which part of my neural network is looking at it. So the weight is a matrix, and then there will be bias that are specific to that part of the neural network. And the whole thing is going through a nonlinear function, activation function. Now you have multiple neurons, and each neuron would have different weight matrix and the bias vector. So what you have is a function that is a nonlinear function that you're writing. So the whole neural network is just a way of expressing a function that can go from complex input to some simple decision making. And the training process is for a supervised machine learning with neural network, you have a label training set. In the case of the food, different families would have standards for what is acceptable situation and what is not. But nobody would try to write out a charter of these are all acceptable conditions when the size of the food is this and the color is that and so on. But rather, most likely, I can be very sure that every family train their children through the repeated experiences that are coming with feedback. So that's a labeled training set. So you're giving experience with a label training set that these are the cases that's okay to eat and these are the cases that are not okay to eat. And you look at the output, and when you see the output coming out of the neural network being the output being different from your desired output, that's the label, you give the feedback that's intended to reduce that cost, the difference between the desired output and the actual output. And when the training is done, we don't know what is the function the neural network has written, but we know it is performing reliably as expected. That is, it is making a sensible decision within our training set. So now we're going to apply that to the STM data. Now the training is going to be done by the theory-guided training set that's been simulated. And once the neural network is trained, we're going to give the real data to the neural network. So we are going to walk through the doping dependence because we are interested in how the dominant motif is dependent or independent of the doping. So this is in the reasonably underdoped setting. What you're finding is when you give this data set with this Fourier transform to the neural network, the most dominant outcome assessment is this period 4 or the category 2. Now we walk up in doping, and again, it remains category 2, period 4. And now we're also noticing the directionality of feeding the data matters. Our simulated data was unidirectional, and the actual data has modulation in both directions. So we try giving the data in one orientation and 90-degree rotated orientation. And what we're seeing in this case is that the two directions are making a difference. That is, the rotational symmetry is broken. Now we keep walking up on the doping with doping, and we are approaching optimal doping. And when we actually go through optimal doping, we find that the different wave vectors, none of them are becoming a clear winner. None of them are dominant and visible. So now, putting all this together and looking at all the different energy layers, we see that not only category 2, the period 4 is most dominant, that dominance kind of really takes off at the pseudogap energy scale, and it comes together with the asymmetry. And based on this, we would say our hypothesis test using the neural network favored the unidirectional, that is commensurate period 4 charge modulations, and all the theoretical work so far points to such modulation being driven by strong coupling physics.
Eun-Ah,
Now,
sorry. Eun-Ah,
yes?
excuse me. There's a question from Florian Marquardt. I'm unmuting him. Please.
Okay.
Thank you. So when you, I think you train on simulated data, right?
Mm-hmm,
and then
yeah.
what exactly is the output of the neural network, or how do you decide what the output should look like? Is it something like binary? This is category 3 or not category 3, or is it more you give weights?
We have 4 output neurons. We had 4 output neurons.
Yeah, and how do you decide for a given generated simulated training example what should be the correct answer?
Our simulation was done with 4 different representative wave vectors. So the simulation sets were produced separately for 4 different labels.
Okay, so each training example only has one of the 4 present.
Yes.
Okay, thank you.
Yes.
Thank you.
So that answered your question?
Yes, absolutely.
Okay. Can I go on?
Yes, please.
All right. So now we're going to switch gears and move to unsupervised machine learning for high volume X-ray diffraction data. This is collaboration with many people, especially my student Jordan Vandely was a key person. Another student, Michael Meddy, worked closely with Jordan Vandely. We had great fun working together with my colleague Killian and his student Jeff in computer science at Cornell. And all the data and a lot of insight about the data and what kind of things matter and what does not matter all came from my X-ray experimentalist colleagues, Jacob Ruff at Chess and Matt and Ray at Argonne National Lab. So we are looking at large volume. This is just giving us a small piece of it because it's just too large to plot. My PowerPoint files have been keep crashing because of the size of my pictures. What we're looking at is this large volume of distribution of intensities as a function of temperature. So if you are making measurements over a range of temperatures, there will be several different temperatures at which we've made the measurement. So we do not only have this large volume data at one temperature, we have a whole series of this large volume data. And I used to call this problem needle in the haystack problem because there is a large volume of data, near a terabyte, but we also know the kind of information that we're interested in that have to do with spontaneous phenomena, emergent interaction-driven phenomena, take up only a small fraction of it. And its main difficulty is in looking for it. But quickly I realized neither myself and most of my audience have much experience with hay. And when we want to talk about what is the difficulty in trying to find something that is rare in this large volume, I thought about illustration that might perhaps be closer to your heart. It's definitely very close to most parents' heart because we have this problem of having a large pile of Lego set. And your kid comes to you or you yourself want to find that special functional piece of rare shape. How should you approach this? And most of you, I think, are not going to choose to pick one piece and look at it one at a time. Or if you've done it once, you will quickly learn that's not a very promising strategy. You get tired, you lose sight of it, and you wouldn't believe what you missed if you try to pick up one thing at a time and look at it. So if that's not what we're going to do with a pile of Lego, we shouldn't be doing that with this X-ray data set either. So what would you do if you have a pile of Lego and you're looking for a special piece? Most people agree that a most effective strategy is to sort, classify. In this case, color is a very nice classifying scheme. But you might have tried a different scheme for sorting, and maybe you find one scheme to be more robust or less robust. So this illustrates that if you want to deal with a large volume data, and if your interesting information is somewhere in rare occurrences, you want to come up with a way of automatically sorting rather than manually sorting. But for Lego, there were some obvious sorting criteria, such as color. What if you don't have obvious criteria for X-ray? So if you don't have, even if you don't have an obvious sorting criteria just because you don't know what to look for, you can still remember that what you're measuring is free amplitude of density. So as you change the temperature, you're looking at temperature dependence of this free amplitude. And we can always remember something very fundamental when we want to think about ordering phenomena. That is, ordering is dictated by Helmholtz free energy, that there is E minus Ts, and it's about the computation between E and S that's guided by temperature. So even if you don't know what to look for, we can expect the different clusters of temperature series among the whole population of Qs can be exhibiting different qualitative behavior, even if we don't know what they are. And the approach that we can use when you want to exploit the differences in some functional dependence and use that as a way of classifying scheme is a time series clustering. So what I'm showing here are 3 different voice trains. This is recorded audio files. And out of these 3, 2 belong to women and 1 belong to men. Or it could be 2 belonging to one person and 1 belonging to another person. Now, how will we look for that? Maybe there is a good way to measure it up, but when we use a time series clustering algorithm and give enough samples to try to sort it out, what it does is to give us this. A time series clustering algorithm can tell us, okay, these 2 belong to the same cluster, and that is different from this cluster. And this is the kind of approach that we want to use. The mission we're after here is to accelerate discoveries instead of weeks and months of manual search that is like looking at one Lego piece at a time. We want to discover models and thereby cluster and accelerate discoveries. Now, the actual X-ray data, it has various challenging aspects that are more challenging compared to the voice train. One of them is that if you look at this this data, this is a raw data plotted, the intensity plotted, and if you look at the scale, it goes over 10 to the 5 magnitude range. There are signals that are 10,000 times larger than other signals. And this kind of distribution makes it extremely difficult to cluster as a raw data. Moreover, there is a lot of noise all over the data. There is a lot of low intensity noise. So some information that's staying sort of more or less low at all temperatures is obviously not of interest to us. Another issue is if you look at the entire momentum space and put a grid and try to keep track of each Q, there are a lot of large part of the data, large part of the momentum space, such as like this area here, actually does not have much intensity. So it's very sparsely distributed. So we make use of we deal with both of these issues by thresholding and rescaling. We threshold based on the average over the entire temperature range and only keep the data set that have significant average with a well thought through thresholding scheme. And after the thresholding, what we're left with is only these Q points to consider as our population to think about. And after rescaling, we have this kind of distribution that's still not obvious to human eye, but something that our Gaussian mixture model successfully sorts. So what is a Gaussian mixture model? If we have Tn temperature measurements, so 1 to n different temperatures, that whole series for a given Q, we treat as an n-dimensional vector. And then we model the distribution of that n-dimensional vector over different points of Q, or the population as we like to think of it, as a multivariate Gaussian. So the properties of the modeling parameters, hyperparameters of this multivariate Gaussian is the mean and covariance. Now we want to think about clusters. So now there won't be only one multivariate Gaussian. We would have multiple multivariate Gaussian. And then we look at the log likelihood defined as the normal distribution function evaluated for a given trajectory at Q with assumed values of mean of given cluster and the variance, and the weight of mixing weight of a given cluster, and summing all of those logs over the Q, different Qs, gives us the log likelihood. We start with guessed values of the mixing weight, mean, and the variance, and the expectation maximization algorithm bring us towards a converged point of learned means and clusters and the mixing weight. And that's how we arrive at the clustering structure. And the only thing that we are setting going in is the number of clusters. So we looked at pyrochlore material, cadmium and rhenium oxide, which has, with this approach, which has two transitions. It has a transition that is second order and another transition at around 113 degrees. And although this is a material that's been known for a little while, it started to gain more traction around 2017 because one of these transitions, the higher temperature transition, 200-degree transition, was detected, the order parameter was seemingly detected by this higher harmonic generation approach. Now, it's been long believed that it is a structural transition that likely going from this pyrochlore, high symmetry pyrochlore state to a state where the two tetrahedras become inequivalent, and further some chirality developing and the bonds within tetrahedra becoming inequivalent. But especially this lower transition is extremely difficult for X-ray to detect because the unit cell size is not changing. It's an example of intra-unit cell order. When we did the clustering, assuming all the points, all the reciprocal space points nearby should belong to the same cluster, which is called label propagation. The result we got is on the left-hand side. This looks very simple, but this is a result of honest processing of 0.5 terabyte of data that only took about 15 minutes. And what's coming out when the whole process is done is these four different clusters. One of them, this red cluster, has obviously order parameter looking dependence to the temperature. And this approach is immediately interpretable because you see the spread and the mean, which is not something that that's put in by hand, but it is a property of the data itself. And when you look at this spread, when the spread is tight, you know this mean is meaningful. And when this mean behaves in this way, such as looking like an order parameter, you know you've discovered an order parameter. Your algorithm does not know about order parameter, but because it's sorting things for you, the data for you in different temperature dependencies, you can immediately discover that you have an order parameter. Now you can look at where these points came from, because each of these trajectories came from different points in Q space. And what you find is that indeed the red points are coming from the Bragg peaks that are expected of the transition that makes the two tetrahedras inequivalent. However, we are seeing very little about the lower transition, although there's a clear thermodynamic signature. So when we wanted to look inside the lower transition, what we did was to open up each Bragg peaks, because lower transition, if the conjectures are correct, would be an intra-unit cell transition. Only thing that can change for intra-unit cell transition is a structure within the Bragg peak. So when we opened up the Bragg peak and redid the clustering, we found this result. Now we are seeing that there are Q points, reciprocal space points, within the Bragg peak, although the Bragg peak is very tight, that are behaving differently. One is going down and some are going up. And we were really puzzled when we first saw this. My experimentalist colleagues couldn't believe it, because, like, you know, this is when you what it looks like when you plot relocate where these trajectories came from in the momentum space. So if you look here, these different colors shows that within the Bragg peak, there were different behaviors. One was going up and the other was going down, just at that transition, at that lower transition point. And we were really puzzled for a while. Eventually, though, we were able to understand what was going on because the algorithm pointed us to where to look at. So now since we've been told that there is something happening inside each Bragg peak, we just looked at it. This is the raw data. And we found, indeed, what's happening is the Bragg peak has a little bit of a width, and that shape is changing. This shift of the weight is clearly coming from the intra-unit cell distortions that are giving this chirality. And when we look at the Bragg peaks that are showing these shifts, we're able to see what happens at each of the two transitions. Now, this figure is given from low temperature up to high temperature at the bottom, which is a little unintuitive. So I want to start from the high temperature. At high temperature, there are no peaks here because the two pyrochlores were equivalent. The high temperature transition hits, and the peaks show up because unit cell size changed. Now, with the lower transition, though, it's not the new peak showing up so much, but the same peak is changing its shape. And this shift of the peak shape is the only way intra-unit cell changes, such as this kind of distortion, can manifest itself. And this was the first time this was detected through X-ray measurements. And the only reason why we could be confident that this is a meaningful thing was because we had statistics over thousands of Brillouin zones. So that's a truly new discovery that we were able to achieve, and we're very excited about this. Now, I think my time is almost up, and I want to have time for discussion, so I want to close now. To summarize, I've talked about machine learning, quantum emergence, and I specifically talked about two examples. One is doing supervised machine learning with simple neural network to do hypothesis testing, especially about the mechanism of charge density wave. And that gave us new insight into this complex data that we don't know how to analyze. And I also talked about unsupervised machine learning, where we were clustering X-ray diffraction data of large volume to make use of, instead of being weighed down by the volume, we were able to make use of the volume by employing the clustering algorithm, which really only works when you have statistics. And we were able to confirm the nature of upper transition and discover signals that were so far unknown as a way of looking for intra-unit cell changes in X-ray data at the lower transition. Now, I want to close by saying that when there is a new tool, there is always a question about, how useful is the tool? Are we going to be replaced by machines? It's a question that I often get when I give colloquium. And I like to say that machines are not only coming, they are already here, and it's your choice whether you're going to learn how to use the machine and do new things that the machine is enabling you to do, or not. So on that note, I would like to thank you for this opportunity, and yeah, thank you for your attention.
Yeah, thank you very much. So here you don't have an applause, but the audience can click a button that indicates that they are applauding, and well, they are. So there is once again, and also thank you for taking the time to deliver your talk. Now that we have a few minutes for the questions, so if there are any, please raise your hands. That was to the audience. And perhaps I could begin. So I would like to understand a bit more, not being very familiar with the field of X-ray crystallography. I'm wondering what is the alternative? Say if they are not, if one did not have the clustering algorithm, what would one do instead?
So so there is a crystallography which is looking for the position of atoms that's going by crystal symmetry, and then there is a whole process of reduction. What we are looking at is less of crystal, say crystal structure, although we are looking at the structural distortion. But the first thing we looked for was, can we quickly find charge density wave, for instance, or some ordering phenomena. And to look for that, the conventional way of doing it is, because it's hard to visualize 3D intensity distribution, and has been no better way than to just visualize. Human researcher looks at it, and that's why I said it takes many months. What you do is you take this, so you take this kind of distribution, and you cannot visualize that. So what you do is you put in a cut. Choose a plane and look at the plane. And in a plane, you can look at the intensity distribution. What you're going to get is something like at the lower left corner here, you get this kind of distribution. And if you were lucky, that choice of plane that you have chosen would have cut the plane where the charge density wave peak is located. Then you will see that show up as you lower the temperature. So you make these various cuts and you observe human eye inspection. That's literally how it's done, human eye inspection. And because human eye inspection is very time consuming, you would try a couple of slices, and if you find it, you're lucky, or if you find what you were looking for, you'll be satisfied. It's very hard to discover what you were not looking for, because there's no way you can exhaustively search this data. As for the intra-unit cell distortion, it is extremely difficult with X-ray, because any intra-unit cell changes are only reflected in the form factor or the phase of the peak. And if you have really sharp peak, there will be no structure visible. And some efforts are to take the X-ray data and to try to Fourier transform it, because Fourier transform of reciprocal space would be something like a real space, but that is also not very easy to interpret. Ultimately, there is the phase problem that when you do X-ray, you lose phase. And that phase is gone, and there's no way to remake it. There are many ways of trying to guess the phase and fit the data, and that's traditional forward modeling, and that's very expensive. So what we're trying to do here is avoid forward modeling on scales of data where it's not possible anyway to do forward modeling, and discover new things. And it's not the final step, but it is the very useful, extremely fast first step. And I'm envisioning that this kind of approach can become a real-time in the middle, during the actual experiment, something that can be adapted, incorporated into facilities.
I see. Thank
Does
you.
that answer your question?
Yeah. That answers pretty much. There's another question from Florian Marquardt. Florian, I have unmuted you.
Thank you. Okay, very great talk and very interesting. So the unsupervised clustering, I'm not familiar with this particular unsupervised clustering algorithm, but I know that in other unsupervised clustering algorithms, there are some parameters that one can play around with, like with DSNE, and then one has to explore a little bit what seems to make sense. So is that the situation also here for this unsupervised clustering algorithm?
So for this so there are unsupervised clustering algorithms. Well, okay, so let me not try to survey, but rather let me just focus on what we're doing here. Gaussian mixture model is an extremely simple model, and that's kind of the virtue of it. And in our approach, the only parameter that we have to play around with is the number of clusters. So if I go back to the log likelihood, so in this log likelihood, you see there is a number of cluster, capital K here. Is this working? Yes. This capital K is the number of clusters. And that's something that we play with, because going in, we don't know how many different kind of behaviors there are. Typically, there would be at least 2 clusters, one being kind of a background and one being something active. But there could be more than one behaviors. And what we, at the moment, what we're doing is we try a couple of different cluster numbers and see whether it makes a difference and when we get a robust clustering. And what's nice about this approach is that together with the clustering, you get the variance. So when you see what are being considered as different clusters, so there is this red cluster and the green cluster. Their means obviously look different, and their variance is pretty tight around that cluster. And that gives us a sense that these are meaningful clusters. Now, with this same data set, if we increase the number of clusters to 8, the algorithm would try to find 8 clusters. But then we will find several of them just lie on top of each other. So then we know that it's not a meaningful, those are not meaningfully distinct. So there's a kind of a feedback mechanism. What we would like to do going forward is to make it automated so that the number of clusters can be kind of optimized automatically, but we don't have that at the moment. But we haven't found it to be, as difficult as dealing with deep neural network with a lot of hyperparameters. We have just one.
Yeah, thank you very much.
It's pretty user-friendly.
Thank you.
All right. Let me see. The time of the talk is now running out, so I would like to thank you again on behalf of both the organizers and the audience. Thank you very much.
All right, thank you.